AS Paper 1, Specimen 2. Question 1. This question is about toxic chloralkane X has a boiling point of 40. Determining the MR by injecting the sample of X into a gas syringe in an oven at 97 degrees C, 100 kilopascals. Results are here. Complete table 1 and table 2. So the mass of the hypodermic syringe before injection, after injection, subtract the two, you'll work out the mass of X injected, 0.270. Volume on the syringe before injection, volume of X in the gas syringe after injection goes up to 105, so the volume of X is 105. X is known to be one of the following. Determine the MR of X and identify which one it is. Give your answer to an appropriate precision. The gas constant R is 8.31. So if you're given a gas constant, you can use PV equals nRT, where you've got pressure, you've got volume, you've got N is the number of moles, you've got the gas constant R, and you've got the temperature in Kelvin. So PV equals nRT. So you could rearrange that. We've got to try and work out N, the number of moles. How do we know that? Because we're given a pressure of 100 kilopascals, we're given a temperature 97 degrees C, we've got the gas constant, and we've got a volume as well. So we've got everything we need apart from N. So we're going to work out N. I could rearrange N, so N would be PV divided by RT. The pressure is 100 kilopascals, but it needs to be in pascals. So if you take a high unit, a large unit like kilopascals, down into a smaller unit like pascals, you multiply by 1,000. So 100 becomes 100,000 pascals. Multiplied by the volume. The volume is 105 centimetre cubed. That needs to be in meters cubed. So centimetre cubed going up into decimetre cubed, you divide by 1,000. Decimetre cubed going up into meters cubed, you divide by 1,000 again. So it's 105 centimetre cubed divided by 1,000 divided by 1,000 again. So that gives us the volume now in meters cubed. So that's pressure times volume, divide by RT to leave N. R is 8.31, and my temperature needs to be in Kelvin. It's given as 97 degrees C, so I need to add on 273, which comes out to 370. I can work out N, 3.41 times 10 to the minus 3. So now I've got the number of moles of gas. So now I can work out MR. So moles is mass divided by MR, so MR is mass divided by moles. The mass is 0.270, and it's in grams. 0.270 divided by the number of moles, 3.41 times 10 to the minus 3, 79.1. I'm looking at the gas constant here, 3 significant figures, so I'll keep this to 3 significant figures. It's difficult to exactly determine how many significant figures you should have it to, because they're all at slightly different significant figures, but I'm going to go with 3 significant figures. That seems reasonable. Suggest a reason other than apparatus inaccuracy why the MR value determined from the experimental results differs from the actual MR. Explain your answer. And this is for 2 marks. So what could have happened? So when we've injected the X into the syringe, into the gas syringe, the syringe might already have a little bit of gas in there. Maybe it's not completely empty. So maybe you've got some air in there as well. So maybe your volume is bigger than expected. So the volume of the gas in the syringe contains X, but probably contains a little bit of air as well, a small amount that's already in the syringe or in the end of the syringe. So V is larger than expected because it's got a little bit of air in there. So now if we look at V being larger than expected, pressure times volume equals N times R times T. So this side is larger than expected because V is larger than expected, then the number of moles is larger than expected. So if the number of moles is larger than expected, then MR is mass divided by number of moles. So MR is mass divided by number of moles. If number of moles is bigger than expected and it's a divide by a big number, then MR is going to be smaller than you expect. Suggest with a reason an appropriate safety precaution could take using toxic chloralkane. You'd put it into a fume cupboard. It's a gas, so you'd use a fume cupboard because it's toxic. It's a toxic gas. Question 2. This question is about enthalpy changes. Write an equation including state symbols. So you have to put S for solid, G for gas, L for liquid, AQ for aqueous or dissolved in water. To show that the reaction takes place when the standard enthalpy of combustion for ethanol is measured. So you have to put ethanol, it's a liquid, plus oxygen, O2, which is a gas, and then CO2, which is a gas, and H2O, which will be a liquid. And then you've got to balance it. So combustion, a reaction with oxygen, and if it's complete combustion, as we'll assume it is, then it makes carbon dioxide and water. State the name given to the enthalpy change represented by the following chemical equation. That's the formation of carbon monoxide from its elements, carbon and oxygen, in their standard states, how you'd find them in the laboratory under normal conditions of temperature and pressure. In other words, carbon is a solid and oxygen is normally found as a gas. So enthalpy of formation, to form carbon monoxide, and 1 mole of carbon monoxide, by the way. Explain why this enthalpy change would be difficult to determine directly, because there's a chance that the carbon monoxide would react with further oxygen and make carbon dioxide. Standard enthalpies of combustion for carbon and carbon monoxide are -393 and -283 respectively. So for carbon it's -393 and carbon monoxide -283. Use this data to calculate the enthalpy change for the reaction in 2.2 here. So the enthalpy change is the sum of the enthalpy of combustion of reactants. Take away the sum of enthalpy of combustion of the products. So you have reactants take away products, and since we're talking about combustion, it's the sum of the enthalpy of combustion of the reactants and the sum of the enthalpy of combustion of the products. Now, for carbon, so enthalpy of combustion of carbon here on the left, it's -393, and enthalpy of combustion of carbon monoxide here on the right, it's -282. So it's take away, subtract a minus. So -393 minus or plus 283 comes out as 110 kilojoules per mole. Use the following data to calculate a value for the xenon to fluorine bond in xenon F4, XeF4, and you've been given 2 equations. You need to form a Hess's law, so Hess's law cycle needs to be drawn, and if you have a look here, xenon gas plus 2F2 to xenon tetrafluoride is -252 in this direction here, going from left to right. And fluorine gas going to fluorine atoms, the enthalpy of atomization from fluorine F2 here to F gas is +158. Now we're breaking up xenon F4 into its atoms Xe and F4Fs here. So it was breaking it up into Xe and 4Fs. Then Xe going to Xe is nothing, so that one is nothing because it's already as it is. So I could break XeF4 up into Xe and 4Fs. I know I've only got 2, I'll come to that in a minute, and that's the enthalpy that we're looking for, the enthalpy of the bond enthalpy. So the energy to break a bond, or those 4 bonds rather. So the 4 bonds, so I'll have to divide by 4 to get one of them. So if I started off with here and went down to here, the other way of doing it is here to here, so it would be +252. This one to here is 0, so I can forget about that. 2F2 to 4Fs, well I've got F2 to 2Fs is +158, so I can double that. So now I've worked out this change here, +252, 0 for this one, 158 multiplied by 2, 568 to turn this XeF4 into Xe and 4Fs. I want the bond enthalpy of one of them, however, so I'm going to have to divide by 4 plus 142. Now bond enthalpy to break a bond, the energy to break a bond, is going to be endothermic. It's going to require heat, take in heat. Suggest a reason why the value in 0.2 differs from the mean XeF4 bond enthalpy quoted in a data source. It's because the mean bond enthalpy is found by taking an average of this in a range of compounds. So it might be Xe to F bond with other atoms bonded around it in another compound. In other words, the Xe to F bond changes depending on what else is bonded to it. So in this case, Xe to F has got 3 other Xe to F bonds around it, but it may not have. So we find the Xe to F bond from a range of compounds and take a mean. So in this case, it might be slightly different than the mean value when we've taken the average of the Xe to F bond enthalpy in other compounds into account as well. Question 3. In terms of subatomic particles, state the difference between the 3 isotopes of magnesium. Well, the reason they've got 3 different mass numbers, and yet they've all got the symbol magnesium, is that they've all got the same proton number or atomic number. They've got the same number of electrons and protons. But the reason they've got a different mass number is because they've got different numbers of neutrons. However, if at all, the chemical properties of these isotopes differ. They don't. They're all the same element with the same number of protons and electrons. They've all got the atomic number 12, or the proton number 12. So they've all got 12 electrons, and that would mean they've got 2 electrons in their outer shell. They're all in group 2. They've all got 2 electrons in their outer shell. So they're going to have the same chemical properties. Mg25 make up 10% by mass in a sample of magnesium. Magnesium has an average mass number of 24.3. So the average of the 24 magnesium, the 25 magnesium and the 26 magnesium is 24.3 because they'll be in different amounts. We know that 10% is 25 Mg, and therefore 90%, the remaining 90%, must be a combination of 24 and 26 Mg. And the average is 24.3. Use this information to deduce the percentages of the 2 magnesium isotopes, the other 2, so 24 and 26. Okay, let's do spoilers and I'll show you through. If we had imagine we have 100 particles. Whenever I find a percentage by mass of a sample, I imagine that I've got 100 particles. If I had 100 particles, then 10% of those particles, i.e. 10, are 25 Mg. So the number of particles of the remaining 2 isotopes, 24 Mg and 26 Mg, must be 90, because 10 add 90 make 100 particles. So we've got 10 particles of 25 Mg and 90 particles of 24 and 26 Mg added together. So the remaining particles, we've got 90 of these 2. We're not quite sure in what ratio amounts we've got them. So let's imagine the number of particles of Mg is x, Mg24 is x, so this is x. So number of particles of Mg26 must be 90 take away x, because 90 take away x plus x equals 90. So I've got x numbers, I've got 10 particles mass 25, x particles mass 24, and 90 take away x particles of mass 26. So the mass of my Mg25, well, I've got 10 particles, each of mass 25, they must equal a total mass of 250. My 24 Mg, well, I've got 24 multiplied by x number of particles, so I've got x number of particles each with a mass of 24, so the mass of those is 24 times x. And the 26 particles, Mg particles, I've got 90 minus x is the number of particles that I've got, multiplied by 26 is 26 multiplied by 90 minus x. So the total mass is the 250, add 24x, and I've expanded, and 26 times 90 minus x. I've expanded this brackets here now, so I've done 26 times 90 is 2340, 26 multiplied by minus x is minus 26x. So now I've added up these two values. 250 add 234, 2340 is 2590. 24x take away 26x is minus 2x. So that's my total mass. The average, which is 24.3, is the total mass divided by the number of particles. Well, we've decided the number of particles was 100, so it's 2490 take away 2x divided by 100. Multiply both sides by 100, or take the 100 up onto the other side, onto the top. 24.3 multiplied by 100 is 2430, is 2590 take away x. So now what I'm going to do is I'm going to take the minus 2x to this side, so it becomes plus 2x, and take the 2430 across the other side, so it becomes minus. So 2x is 2590 take away 2430, 160. So 2x is 160, x is 80. So my number of particles of mg is x, so that's 80. So 80 out of the 100, or 80%, is 24, and therefore 10% must be 26, because these two added together make 90. So if mg24 is 80, mg26 must be 10 to make 90. In a time-of-flight mass spectrometer, ions are accelerated to the same kinetic energy, where kinetic energy is half mv squared. V is the velocity of the particle, m is the mass of one particle, just one particle in kilograms. One particle in kilograms, the kinetic energy will have been given. We've also got velocity as distance divided by time, and we've been given the kinetic energy, the time of flight, and Avogadro's constant. So first of all, let's do spoilers again. 25 mg, 1 mole is 25 grams. So I've got 20, if I've got 1 mole, I've got 25 grams. In 1 mole, there are 6.022 times 10 to the power 23 particles. So 25 grams, to get grams up into kilograms, you divide by 1,000. To get grams up into a larger unit value of kilograms, divide by 1,000, 0.025 grams. Now that's the mass of 1 mole, and we know that there are 6.022 times 10 to the power 23 particles in a mole. So I'm going to divide this number by 6.022 times 10 to the 23. I've got now the mass of just one particle in kilograms, 4.15 times 10 to the minus 26. That's my m value here. Kinetic energy is half mv squared. I've got kinetic energy, I was given it in the question, 4.52 times 10 to the minus 16 equals half, multiplied by 4.15 times 10 to the 26. That's m, the mass of one particle in kilograms, multiplied by v squared. I'll just multiply out this half here, so 4.52 times 10 to the minus 16 is 2.075 times 10 to the minus 26 times v squared. Take this across onto the bottom, or divide, so take it across the equal sign and put it on the bottom. 4.52 times 10 to the minus 16 divided by 2.075 times 10 to the power 26 is v squared. That equals 2.18 times 10 to the power 10. To get v, I square root it. 1.48 times 10 to the power 5. I've now got v. I've also got t. I've been given t, so I can work out d. v equals d divided by t. v is 1.48 times 10 to the 5 equals d divided by t. t is 1.44 times 10 to the minus 5. I've been given that in the question. So d are these two numbers multiplied together, 2.13, and it'll come out in meters, 2.13 meters. Question 4. A sample of strontium ore, so an ore is a chemical that we dig from the ground, it's obviously got strontium in there, is known to contain some strontium oxide, some strontium carbonate and some impurities. So what they've done is they've taken a mass of a crucible, that's the vessel that they're going to heat it up in. The mass of the crucible and the ore is 16.11, so if I subtract those two I can work out the mass of the ore on its own. They've heated it up and they've found that the mass goes down. So let's have a look at the chemical equation. Some of the strontium carbonate in there, SrCO3, turns into strontium oxide and carbon dioxide. And carbon dioxide is a gas, so that's going to escape to the air and it's going to have some mass. That's why the mass is going down, because I'm losing some mass when this gas is made and it's escaping into the atmosphere. Use the data to calculate the mass of strontium carbonate in the original ore sample. Give your answer to the appropriate precision. Well, if I take the mass of the crucible here and the ore, and the mass of the crucible after heating, and I subtract the two, I'll work out the mass of the carbon dioxide that's made. I have to carry on until it's heated and it doesn't lose any more mass, because then I assume that all of the strontium carbonate's reacted and it's finished, the reaction's finished. So that's 14.58 at the end. It's still releasing some carbon dioxide here, but at the end 14.58, and it stays as 14.58. All the carbon dioxide's reacted. So 16.11 take away 14.58 will give me the mass of the carbon dioxide that's made. And if I can work out the number of moles, I can work out the number of moles of strontium carbonate and the mass of that. I'll show you what I mean. So 16.11 take away 14.58 is the mass of the carbon dioxide. 1.53 grams of carbon dioxide. Now I know carbon dioxide, carbon's a mass of 12, oxygen's a mass of 16, so I've got 12, add 2 16s. 44 is the mass of carbon, is the MR of carbon dioxide. Moles is mass 1.53 divided by 44, 3.48 times 10 to the minus 2 moles of carbon dioxide are made. Now in this equation, 1 mole of strontium carbonate makes 1 mole of strontium oxide and 1 mole of carbon dioxide. So 1 mole of strontium carbonate makes 1 mole of carbon dioxide in equal amounts. But I haven't got 1 mole of carbon dioxide made, I've got 3.48 times 10 to the minus 2 moles made. Therefore I must have 3.48 times 10 to the minus 2 moles of strontium carbonate. I can work out the MR of strontium carbonate, and it comes out as 147.6. Moles is mass divided by MR, so mass is moles multiplied by MR. 3.48 times 10 to the minus 2 moles multiplied by 147.6. 5.13 grams is the mass of my strontium carbonate. Each balance reading has an uncertainty of 5.00 milligrams. Remember, a milligram, to get it into grams, because we're working in grams here, so let's get this into grams. To turn milligrams into grams, a small unit value into a large unit value, I divide by 1,000. So 5 divided by 1,000 is 0.002. But I have two balance readings, one at the beginning and one at the end, and I'm subtracting the two, one from each other. So I've got two balance readings. My error is not 0.005, it's 0.005 multiplied by 2. So my error is 0.01. That's my error. So that's how far my readings could be out. I divide by the mass that I've taken. 6.26 is the mass of the ore sample. 6.26 is the mass of the ore sample. 16.11 take away the mass of the crucible, 9.85 is the mass of my ore sample. So 0.01 is the error. 6.26, sorry, how far out the readings could be. 6.26 is the value of the amount of strontium ore that I have, multiplied by 100%. 0.160% is my percentage error. The mass of the inert impurities in the sample was 347 milligrams, or 0.347 grams. To turn milligrams into grams, remember you divide by 1,000. Deduce the mass of SRO in the sample and justify any assumption made in calculating your answer. So what I've got is, I've got 6.26 is the original mass of the ore. Subtract the mass of the impurities. Subtract the mass of the strontium carbonate, because remember the ore here, 6.26 grams of ore, has got three things in it. It's got impurities, 0.347, that it tells you here. Converted this into grams by divided by 1,000. Strontium carbonate, which we've worked out is 5.13 grams, and the remainder then is strontium oxide. So if I subtract the mass of the impurities and the mass of the strontium carbonate from the original mass of the ore, it will tell me the mass of the strontium oxide that was in the original sample, 0.783 grams. Strontium metal can be extracted, that means taken out, by heating strontium oxide with aluminium metal. In this reaction, strontium vapour, so a gas, and solid aluminium oxide are formed. Write an equation for the reaction and state the role of the aluminium in the process. Explain why strontium forms a vapour but aluminium oxide is formed as a solid. So I've got strontium oxide. I know strontium oxide is SRO. It even tells me that in the question. So SRO plus aluminium. I'm going to make strontium vapour, so that's SR, and my remainder, I've got aluminium oxide. Oh, sorry, here. Justification that, any assumptions that I've made, the strontium carbonate reacts because it's heated to a constant mass. So it stopped reacting and all of the strontium carbonate has reacted because the mass isn't changing. In other words, all the carbon dioxide's made. Equation then here, strontium oxide, aluminium is Al. How do I know that aluminium oxide is AlO2? Well, aluminium's in group 3, so it'll form 3 plus ions. Oxygen is in group 6, so it'll form 2 minus ions. So I need 2 3 pluses and 3 2 minus to balance out and leave no charge left over. And I end up with SR gas, SR vapour on its own. And then I'm going to balance it up. So I've got O3, so I need 3 SROs to make the O's balance. 3 SRs, I'll need 3 SRs, and therefore 2 ALs here. Role of aluminium, it's removing oxygen. Something that removes oxygen is a reducing agent. So this SRO has been reduced. It's lost oxygen in going from SRO to SR. So the other chemical in there is the reducing agent. It's causing this to be reduced. The other way of looking at it is that oxygen is in 2 minus oxidation state. SR must therefore be in plus 2 oxidation state. It's in group 2 after all. So it's going from plus 2 to an element on its own where it's in 0 oxidation state. It's going from plus 2 down to 0 oxidation state. It's been reduced. It's a reducing agent, is the aluminium, causing the SRO to be reduced to SR. Explanation of why this has got why this is a solid and this is a vapour. Well, this is ionic, so it's got 3 pluses and 2 minuses. It's an ionic lattice. It's got ionic bonding, whereas this is a metal on its own. It's got metallic bonding with weaker bonds. So SR is collected as vapour because Al2O3 is an ionic lattice with ionic bonding, strong ionic bonding, whereas SR is metallic with weaker metallic bonding. Question 5. The student was given a 50-gram sample of solid silver chloride contaminated with solid silver carbonate. The student suggested the following method to obtain the maximum amount of pure dry silver chloride from the sample. So what do we know about this first of all before we have a look at the student's method? We've got a 50-gram sample of solid silver chloride. That's quite a lot. Remember, a gram is about the size of a Smartie or an M&M, so 50 of those is going to fill up a boiling tube pretty much. So tip the solid into a boiling tube. I would suggest you use something like a 250 milliliter beaker instead to give yourself a little bit more room. Add dilute nitric acid. Well, it says here that you've got solid silver carbonate, so it's a good idea to add some acid, because an acid would react with the carbonate and remove the silver carbonate. It would make carbon dioxide, as all carbonates do with acids. However, it says you want to make some silver chloride, the maximum amount of silver chloride, so silver carbonate and nitric acid would make silver nitrate. Surely if you use hydrochloric acid to make silver chloride, it would turn the silver carbonate into additional silver chloride to maximize the yield. So I would suggest that you add nitric acid. It doesn't say how much nitric acid, so how do you know that all the silver carbonate's been used up? I would add an excess of hydrochloric acid. I've got hydrochloric acid available there. I'd use an excess until all the bubbles of carbon dioxide have been made, and then you know that all the silver carbonate's been used up. You haven't got that as an impurity at the end, and you've maximized the amount of silver chloride that you've made. Allow the remaining solid to settle. Decant off the liquid means just pour off the liquid. Well, that's not going to be very efficient, because decanting the liquid isn't as good as something, say, for example, like filtering, where you're going to remove all of the solid. Decanting the liquid, sometimes some particles of solid are removed with the liquid as well. And also, it doesn't dry it off as well, so and you've not got an opportunity to wash it. So I would be filtering it, washing it and drying it, leave the sample to dry at the end. So let's have a look at this. Boiling tube likely to do too small, yes. Use a 250 milliliter beaker, a medium-sized beaker, or would any kind of medium-sized beaker. Use hydrochloric acid instead of silver nitrate to make maximum amount of silver chloride. Use excess acid until no more bubbles are made to make sure that all the silver carbonate's used up. Decanting means you've got a wet solid, and you're also going to lose some of the solid as well. Instead, use a filter and then washed with distilled water. Distilled water is a good idea. Distilled water hasn't got any particles in there, any impurities in there, and therefore distilled water would mean that you're not recontaminating the solid. And then dry, but it already says dry. Question 6. This question is about the elements of group 7 of the periodic table and their compounds. Bromine. So Br2 is just 2 bromine molecules bonded together. Bromine's in group 7, both atoms wanting to gain 1 electron, so they'll share 1 electron each in a covalent bond. It'll be molecular, so they'll just be Br2 molecules together, bonded intermolecularly by van der Waals bonds. Strontium chloride SRC L2. So you've got strontium in group 2 and chlorine, 2 chlorines in group 7. So the strontium will want to lose 2 electrons, each chlorine will want to gain 1 electron, so the strontium will donate electrons to the Cls. So Sr will become Sr2+, Cls will become Cl-. There'll be ionic bonding, strong ionic bonding in a lattice in that. And the iodine monochloride, ICl. Well, chlorine's slightly more electronegative than iodine. It's smaller and so withdraws electrons towards itself more readily. So that'll have a slight delta minus charge, and the iodine will have a slight delta plus charge. So you'll have polar bonds within the ICl molecules. And so between one ICl molecule and another ICl molecule, the intermolecular bonds will be dipole-dipole attractions. Suggest with reasons the order of the melting points. Well, the one with the highest melting point is going to be strontium chloride, SrCl2, because it's ionic in a strong ions held together, strongly attracted in an ionic lattice. Next will be ICl, because there's some electronegativity in the Cl, so it's electronegative, so you get polar bonds, delta pluses and delta minuses, delta plus on the I, delta minus on the Cl, and so those polar bonds will create dipole-dipole attractions between the molecules, intermolecular bonds, so I have relatively strong intermolecular bonds, whereas Br2 is just molecular, with van der Waals bonds weaker, and therefore the lowest boiling point. Write an equation for the reaction of chlorine with cold water. Well, you just got to learn this really. This happens in swimming pools and in drinking water. Chlorine in water forms HCl and something called hypochlorous acid, HClO, which kills bacteria. A disadvantage of treating water in this way. Well, you want to kill bacteria so that when you drink it, it doesn't harm you. But a very small percentage of the water is actually drunk. Quite a lot of it's used for washing clothes, flushing toilets, watering plants, etc. So most of potable water is treated water. Water that's been treated with chlorine is not used for drinking. Bromium reacts with phosphorus to form phosphorus tribromide. Write an equation for this reaction. So we've got Br2 and P4. Phosphorus forms at P4. So don't write just phosphorus on its own. Always put P4. It forms a molecule. It's molecular P4. 4 phosphoruses bond together. So Br2 and P4. It says it makes phosphorus tribromide. So Br3 tribromides, 3 Brs, and therefore P4 you're going to need 4 Ps, 4 P Br3s to balance up the 4 Ps, and 12 Brs, so you need 6 Br2s. What's the shape of PBr3? Well, let's have a look. So phosphorus is in group 5 of the periodic table. 3 of the electrons will bond and form 3 bonding pairs, and therefore you've got 2 electrons left over, 1 lone pair. So if it were tetrahedral, if it were 4 bonding pairs, the bond angle would be 109.5. Every time you replace a bonding pair with a lone pair, you reduce the bond angle down by 2.5. So 109.5, take away 2.5, leaves 107. Now you actually don't look at the lone pair of electrons when you're actually discussing the shape. So it's a trigonal pyramid shape with 3 bonding pairs and 1 lone pair. What's the bond angle? Well, it's actually slightly lower than 107.5 because the BRs are slightly larger and therefore trouble to fit close to each other. But if you go with the rule of 109.5 for tetrahedral, and every time there's a lone pair you remove 2.5, so it becomes 107. It fits within the acceptable range. Phosphorus pentabromide in solid state makes PBr4 plus and Br minus ions. Draw the shape of PBr4 plus and suggest its bond angle. Let's have a look then. So phosphorus is in group 5. If it's got 5 electrons in its outer shell, if it's plus charge, then it's lost an electron. So instead of 5 in its outer shell, it's now only got 4 in its outer shell. 4 Brs form 4 bonding pairs. These repel equally, and so there's 4 bonding pairs, no lone pairs, into a tetrahedral shape. Remember, if you get more than 3 bonding pairs, then it starts to not be planar anymore and starts to form a 3D shape, with some exceptions like xenon tetrafluoride, etc. But most of the time, after 3 bonding pairs, then it starts to form a a non-planar shape. So we've got bond angle 109.5. Question 7. Which is the correct classification for the element yttrium with the symbol Y? So yttrium has its transition metal. It's in the transition metal block. It's sometimes called a D block element because it's got partially filled D blocks, a partially filled D orbital, a transition metal. Answer C. Question 8. Which of the following is a correct statement about the trend in atomic radius across period 3 of the periodic table? So atomic radius is the distance from the nucleus to the outer electrons. If you're in the same period, then you can get, you've all got, in period 3, they've all got 3 electron shells, so you're not getting any increased number of shells, you get no change in shielding. All you're getting is, across the periodic table from left to right, the proton number increases, so the number of protons increases left to right, so you're getting more and more protons in the nucleus, so you get an increased nuclear charge or increased nuclear attraction, and therefore the atomic radius is going to decrease as you get more and more protons going left to right across the period, and there's increased nuclear charge or increased nuclear attraction. The answer is B. Question 9. A measuring cylinder has an uncertainty of plus or minus 5 cm³. That means how far the reading could be out. Now, how many measurements do you take in a measuring cylinder? 1. So you multiply this by 1. So 1 reading, it could be out by 5 cm³. If it was something like a burette where you're measuring 2 readings, you'd multiply the uncertainty by 2. Same on a thermometer where you're measuring start and end, where you're measuring a temperature change, say for example, you'd multiply the uncertainty by 2. So you multiply the uncertainty by the number of measurements you would take. So something like a measuring cylinder, something like a balance, you multiply by 1 reading. Something like a burette, start and finish, or a temperature change on the thermometer, start and finish, you'd multiply by 2. So the error is 5 cm³. The problem is that each of these volumes are in decimeter cubes, so we need to convert these into centimeters cubed. So to convert a large unit value like a decimeter cube down into a centimeter cube, you multiply by 1,000. So 0.025 decimeter cubed is 25 centimeter cubed, 0.25 decimeter cubed is 250 centimeter cubed, 2.5 decimeter cubed is 2,500 centimeter cubed, and 25 decimeter cubed is 25,000 centimeter cubed. Then what you do is you take once you've converted them all, you take the 5, which is how far out it could be, divide by the volume and multiply by 100%. So your answer is C. So if you note, actually, the larger the volume that you're measuring, the lower the error, because it's the uncertainty divided by the volume that you're measuring out, multiplied by 100%. But your answer is C. Q forms a sulfate with the formula QSO4. Well, you need to know what a sulfate ion is. It's SO4 2-. Which of these could represent the electronic configuration of Q? So if SO4 is 2-, Q must be 2+. 2+ and 2- to leave no charge left over. So Q is in group 2. It's something probably like magnesium or calcium. It's going to have 2 electrons in its s level in its outer shell. It's going to have 2 electrons in its third energy level. Which equation represents a reaction which does take place? Well, as you go down the periodic table, the halogens become less and less reactive. So fluorine at the top is the most reactive, then you go down to chlorine, which is the next reactive, then you go down to bromium, which is next reactive, then you go down to iodine, which is next reactive. So will chlorine displace iodine from sodium? The answer is A, yes. Bromine is lower than Cl, so it won't displace it. Chlorine, sodium chloride and water just dissolves. Actually, it doesn't even react, and this one would make sulfuric acid would make water here. So hydrochloric acid and sulfuric acid, actually, I don't think that would react at all. Following the equilibrium was established in a container with volume V centimetre cubed at 393 Kelvin and 200 kilopascal, which would increase the yield of RM2. So how are you going to make RM2? How are you going to make more RM2? Well, you could increase the concentrations of M2 and R, and then by Le Chatelier's principle it would try and lower the concentrations of M2 and R by reacting it to make more RM2. You could remove some RM2 as it was formed by Le Chatelier's principle. It would try and make some more RM2, because it would oppose the change. If you're removing the RM2, lowering its concentration, then by Le Chatelier's principle it would try and oppose that and make more of it. Let's have a look. It's an endothermic reaction, so it takes in heat when you go to the right hand side. So if I increase the temperature by Le Chatelier's principle, it will try and lower the temperature and shift to the right hand side to try and lower the temperature of the surroundings. So increase in temperature would make more RM2. You can increase pressure. That would make more RM2 because you've got 2 moles on the left and 1 mole on the right. So increase in pressure by Le Chatelier's principle, it will try and lower the pressure by lowering the volume and shift the equilibrium to the right hand side and make more RM2. You could increase the pressure by decreasing the volume. So decreasing the volume would increase the pressure as well and shift the equilibrium to the right hand side. So changing the pressure to 150 pascals, lowering the pressure, no, we would have to increase the pressure. Change the temperature to 293 from 393, in other words, lower the temperature. No, increasing the temperature by Le Chatelier's principle would move it to the right hand side because it would try and lower the pressure, lower the temperature by Le Chatelier's principle to oppose that change and shift to the right hand side. So increase in temperature would shift it to the right hand side, not decrease in temperature. Remove RM2 as it is formed. Yes, the answer is C. Change the volume of the vessel to double the volume. Double the volume would be lowering the pressure because there'd be more volume. Lowering the pressure now would shift it to the left hand side. Your answer is C. Which of the following shows nitrogen its correct oxidation states in the compounds given? So in NH3, hydrogen's in oxidation state +3, hydrogen's in its oxidation state +1, 3 1s are 3, so the 3 H's are +3, so the nitrogen's in -3. So it's either B or C. Oxygen is in -2, so there's no charge left over, so the 2 N's are +2, so each N is in +1. So again, it's either B or C. In this one, we've got 2 oxygens in -2 because it's in group 6, forms 2 minus ions, so 2 minus 2 is a -4. Hydrogen is in +1, so -4 + 1 is +3, so the nitrogen must be in -3 because -3 + 3 leaves no charge left over, so the nitrogen is in +3, which is answer B. Question 14. What is the volume of 0.2 mole per decimeter cube barium hydroxide required to neutralize exactly, so we want the same number of moles, 30 centimeters cubed of 0.1 mole per decimeter cubed hydrochloric acid? So I've got a volume and I've got a concentration of hydrochloric acid. I can work out the number of moles, and the number of moles of barium chloride, as long as it reacts 1 to 1, we'll have to look at that, 1 mole to 1 mole would be exactly the same. Let's work out the number of moles of hydrochloric acid first of all. I've got 30 centimeter cubed. I've got to get into decimeter cubed because concentration is moles divided by volume. So moles is concentration multiplied by volume. So the number of moles is 0.1 is the concentration. The volume is centimeter cubed up into a higher unit value of decimeter cubed. I divide by 1,000. So 0.1 multiplied by 30 divided by 1,000. I've got 0.003 moles of hydrochloric acid. Now the same number of moles of barium hydroxide would react, and the number of moles of this would be the same, as long as 1 mole of barium hydroxide reacts with 1 mole of hydrochloric acid. So how do I know that? Well, I have to write an equation, or at least think about the equation. Barium hydroxide, look, hydroxide is an OH minus ion. Barium is 2 plus because it's in group 2 of the periodic table. It forms 2 plus ions. So an OH 1 minus ion, I'm going to need 2 OHs. A Cl, when it forms barium chloride with hydrochloric acid, barium 2 plus, Cl is in group 7, so it gains 1 electron, so that's minus 1, so I'm going to need 2 Cls, 2 1 minuses to cancel out the Ba2 plus and leave no charge left over. So if I've got 2 Cls for every Ba, I'm going to need 2 HCl. So it's not 1 to 1. 1 mole of barium hydroxide does not react with 1 mole of hydrochloric acid. 1 mole of barium hydroxide reacts with 2 moles of hydrochloric acid. So I've worked out the number of moles of hydrochloric acid, 0.003, but 2 moles of hydrochloric acid react with 1 mole of barium hydroxide, 2 to 1. So I need to divide this value 0.003 by 2, divide it by 2, because I've got half the number of moles of barium hydroxide that have hydrochloric acid. So I take the hydrochloric acid, divide it by 2, I've got 0.0015 moles of barium hydroxide reacting. So concentration equals moles divided by volume. So volume equals moles divided by concentration. Number of moles is 0.0015 for the barium hydroxide. My volume is my concentration is 0.2, so divide by 0.2, 0.0075 decimeter cubed. It wants it in centimeter cubed, so decimeter cubed down into a lower unit value of centimeter cubed, I'll multiply by 1,000, 7.5 centimeter cubed. The answer is D. Which reaction has the largest atom economy for the production of hydrogen? So what I've got to do is, for the to work out the atom economy, then I work out the relative formula mass of the products. So the relative formula mass of the products for each of these, I've got a CO and an H2 rather. So I've got a 12, I've got a 16, H is a 1, so that's 2, 30. ZnCl2 is a 65, add 2 Cls, which are 35.5s, add 2 1s, which is 2138. A carbon monoxide is a 12, a carbon, add an oxygen is a 16, add 3 H2, so that's 6 H's in there, so that's each H is 1, works out as 6, 34. CO2 is a carbon, add 2 oxygens at 16, and an H2 is 2 1s, is a 2, is a 46. Which has the largest atom economy for the production of hydrogen? So I look at hydrogen here and I see how much hydrogen is made. So what is the fraction, the MR, of the hydrogens that are made? 2 1s is 2 here, 2 1s is 2 here, 6 1s is 6, 2 1s are 2 here. So I take the fraction of hydrogen's MR, 2, 2, 6 and 2, and I divide by the MR of all of the products, and my answer is 6. 6 divided by 34 is the highest of each of these fractions. My answer is C. Which is the best oxidizing agent? Well, remember oil rig, oxidation is loss. Loss of electrons, so the oxidizing agent causes this oxidation. So an oxidizing agent causes oxidation. It's making something else in the reaction oxidized. So the oxidizing agent, whichever one of these, is causing the other reactant, the other thing in the equation, the other thing that's reacting, to be oxidized. So it's causing the other thing to lose electrons. So if it's causing the other thing to lose electrons, it itself must be reduced. It must be gaining electrons. So the oxidizing agent is itself reduced. It gains electrons. So which of these is most readily able to gain electrons? Well, it's not B or D, they've already gained electrons. Is it A or is it C? Is it Cl2 or is it Br2? The answer is A, Cl2, because it's smaller, so it's got a greater nuclear attraction. So Question 17. Which of these correctly shows the number of subatomic particles in a 41 potassium plus ion? So you can look at potassium and you could find that its proton number is 19. So it's got 19 protons and 19 electrons. However, if it's become plus charge means it's lost an electron. So it's not got 19 electrons anymore, it's only got 18 electrons. So it's still got the same number of protons. The plus charge means it's lost an electron. So 19 for potassium is always going to be 19 for potassium. This top number with isotopes can change the number of neutrons, but the bottom number, the proton number, is always going to be 19. So I've got 19 protons. I would have 19 electrons as well in a potassium atom, but it's a potassium ion formed a plus charge, so it's got 18 electrons. So automatically my answer is C. I could work out the number of neutrons by subtracting the 41, subtract the 19 would be 22, just to double check, but my answer is C. After a reaction of some zinc metal with excess sulfuric acid, a student collected 40.8 of these crystals. The yield of the crystals was 70%. So first of all, I'd be thinking, well, how much would they have made if they'd made 100%? What's the easiest way of doing that? Well, 40.8 is 70%. So if we divide by 70, 0.583 is 1%. So 100%, and multiply 0.583 by 100 to get 100%. 58.3 is 100%. That's the amount that could have been made had some not been lost. So the amount that I could have made is 58.3 had I not lost some along the way. The MR of this zinc sulfate is 65 for a zinc, 32 for an S, 4/16 for the oxygen, and I've got 7 lots of water. Water is 2 1s for the H's and a 16 for the O. 18 is water, and I've got 7 18s. 289 is the relative formula mass of zinc sulfate, and I've got the mass that I've made. I've got the MR, so moles is mass divided by MR. So the number of moles is 58.3. That's how much I could have made had I not lost any along the way. Divided by 289, I could have made 0.20 moles. So there's one ZN in there, so if I'd reacted it with some water and something like sulfuric acid, I would have used 1 mole of zinc, except I didn't make 1 mole of zinc sulfate crystals. I only made 0.2. So 0.2 moles of zinc, the same number of moles, are going to be needed. MR of zinc is 65, look that up in a periodic table. Moles is mass divided by MR. So mass is moles multiplied by MR. 0.2 moles multiplied by an MR of 65, 13.3 grams. My answer is B. Question 19. Which of these are redox reactions? So it has reduction and oxidation. So you've got to look for the obvious answer. The obvious answer is D. So the obvious answer, D, has magnesium. Magnesium on its own in oxidation state 0 goes to MgS. Now in MgS you've got magnesium sulfide. So Mg has become 2 plus, as it's given 2 electrons away to the S. S is in group 6, so wants to gain 2 electrons. Mg is in group 2, so wants to lose 2 electrons. So the Mg will give 2 electrons to the S and form an ionic bond. Mg2 plus S2 minus. So the Mg has gone from 0 oxidation state, not bonded to anything, it's got no charge, 0 oxidation state, to 2 plus 2 oxidation state. So that has gone from 0 up to plus 2, it's been oxidized. The S has gone from 0, just on its own, an element on its own with no charge, 0, to S2 minus, because it's in group 6 and gained 2 electrons, taking them from the Mg. 2 minus, gone from 0 down to minus 2, that's been reduced. So you've got oxidation and reduction, so that's the obvious answer, D. And so I'd ignore some of these more complicated equations here and look straight to D. 2.4 grams of an explosive, J, contains certain number of grams of nitrogen, certain number of percentage of carbon, percentage of hydrogen, the remainder of J is oxygen. I need to get these into all into percentages, all into the same units, so I can work out the percentage of nitrogen in the 2.4 grams. I've got 0.473 grams out of the 2.4 grams. I've got 0.473 divided by 2.4 multiplied by 100%, it gives me the percentage of nitrogen in there. So now I've got percentages, the remainder is oxygen, so I can do 100, take away the 19.71 which is nitrogen, take away the 33.8 which is carbon, take away the 1.41 which is hydrogen. And it tells me that 45.08%, the remainder, is oxygen. I divide by the masses of each of the atoms to get the ratio of the amounts. So 19.41 divided by 14, and a mass of nitrogens are 14. 33.8 divided by 12, the mass of a carbon is 12. 1.41% divided by the mass of a hydrogen, which is 1. And 45.08% for the oxygen divided by the mass of an oxygen, which is 16. Gives me these ratios, 1.41 to 2.82 to 1.41 to 2.82. To get the simplest ratio, I divide by the smallest number, so I divide all of them by 1.41. It comes out as 1 to 2 to 1 to 2. So the number of nitrogens is 1, the number of carbons is 2, the number of hydrogens is 1, and the number of oxygens is 2. The answer is C, C2H1N1O2. Question 21. What's the number of atoms in 0.01 moles of NH3? Well, first of all, I just want to point out that that's called a particle or a molecule. So NH3, so this Avogadro's constant tells you the number of NH3s, particles or molecules, in a mole, but it doesn't tell you the number of atoms. Atoms are the individual parts of this, so I've got 1 N and 3 H's, so I've got 4 atoms in a particle or in a molecule of NH3, so my final answer must be multiplied by 4 to convert the number of particles or molecules into atoms. Anyway, let's have a look. So, what does Avogadro's number tell you? The 6.022 times 10 to the 23 tells you number of molecules or particles of NH3 in 1 mole, but I haven't got 1 mole, I've got 0.01 moles. So 0.01 moles contains 0.01 multiplied by 6.022 times 10 to the 23 molecules of ammonia, which is 6.022 times 10 to the power of 21. So a hundredth, I've got a hundredth of the number of molecules that I had in 1 mole, but NH3 contains 4 atoms, so I've got this number of molecules of NH3, but every NH3 contains 4 atoms, so I need to multiply it by 4. The answer is 2.41 times 10 to the power of 22. The answer is D.